Students, in this video lecture, we are going to understand of the complex random processes and discrete random processes. In the earlier video, I have given introduction about the Gaussian random processes and the Poisson random processes. Okay, so this one is the continuation of the earlier video only. So here we are going to start with complex random processes and we are going to understand a problem. Then we will move on to the introduction to the discrete random processes. Okay, so this complex random processes, say for example, you are having a random process z of t is a complex, you will call z of t is a complex random processes. If we are having a real part which is also a complex which is a random process, and the imaginary part is again a random process. So z of t is equal to x of t plus j y of t. Here x of t and y of t are two independent wide sense stationary random processes. So here I am very much specific about wide sense stationary random processes. That is why, because like in complex, if you go for a general thing, there are so many other things to understand also. So let us restrict ourselves only to wide sense stationary random processes. So please understand, x of t and y of t are two different random processes because it is completely independent and it is also wide sense stationary. These two random processes combine together in the complex form like x of t plus jy of t to form a complex random processes. So z of t is a complex random processes. So if you want to find mean of z of t, okay, mean of z of t, what you can do, you can take expected value of z of t, which is nothing but expectation of x of t plus j y of t. As you know, x of t and y of t are two independent random process. This can be separately written as expectation of x of t plus j expectation of y of t, and it was given x of t and y of t are wide sense stationary. So what is x of expectation of z of t is nothing but x bar plus j y bar. Okay, similarly, if you want to find autocorrelation of z of t, we write this as r z of t comma t plus tau, which is nothing but r z of tau. Why? Because obviously this is wide sense stationary, so the result will also be depending only on time difference, not on absolute time. So which is nothing but expectation of z star of t. Star is nothing but complex conjugate of z multiplied by z of t plus tau. Expectation of z star of t multiplied by z of t plus tau. Similarly, autocovariance C z of t comma t plus tau can be written as C z of tau only, because this again will be depending only on tau, which is nothing but r z of tau minus z bar the whole square. Okay, so this is autocovariance. Now, if you have two complex random processes, say for example, if we have two complex random processes, zi of t and zj of t. Okay, so if zi and zj, that is zi of t and zj of t, are uncorrelated, you very well know there is no relationship between both the things, are uncorrelated. Under this case, you will find r zi zj of tau will be 0. Correlation is completely 0. Similarly, if zi of t and zj of t are orthogonal, orthogonal is nothing but both are traveling in two different directions. Under this case, you will have Czi, Czj of tau will be equal to 0. That is, covariance will be equal to 0. Okay, so these are two special cases if you are having two different random variables. Next is, if you want to understand the power spectra or power spectral density, of complex random processes, as we are talking only related to the Whiteson stationary complex random processes, what you can do is you just take a Fourier transform of the autocorrelation function, you will be getting the power spectral density. So what is autocorrelation function? R z of tau is the autocorrelation function. To get the Fourier transform, what you need to do, you multiple R z of tau with e power minus j omega tau. We are going to eliminate tau, therefore you have to integrate with respect to tau for all the ranges of tau, so that you'll be getting rho z of omega. Similarly, if you take inverse Fourier transform of rho z of omega, that is multiple rho z of omega with e power plus j omega tau. Now eliminate omega for all the ranges of omega, 1 by 2 pi. You should be getting r z of tau. This is about the power spectral density of the complex random processes. Okay, so now the next thing is nothing but a problem. Let us see a problem. Just 1 minute, let me check whether I'm recording the session or not. Okay, so I'm recording the session. Now let us do one problem. So please carefully understand. We are measuring the voltage, okay, across a load. It's given by a complex random processes. You can see V of t is given by summation n equal to 1 to capital N, a n e power j omega naught t plus theta of n. So you can write like this actually, e power j of omega naught t in the numerator, no, e power, write like this. Okay, or let me write it here. V of t is nothing but summation n equal to 1 to capital N, a n e power j of omega naught t plus theta n. It's a complex random processes. Here a n is a random variable. Okay, there is no description given about the a n, and theta n is a random variable, but they have mentioned theta n is uniformly distributed in the interval of minus pi comma plus pi. What is the question? Question is to find the autocorrelation function and the power spectral density of the V of t. So let us do the solution now. Okay, so we want to first autocorrelation function. So RVV of t comma t plus tau can be written as expectation of V star of t multiplied by V of t plus tau. V star in the sense complex conjugate, right? So here you are having plus j, you have to put minus j here. Okay, so RVV of t comma t plus tau, expectation of, you have summation, right? So put summation n equal to 1 to capital N, a n e power minus j omega naught t plus theta n. Okay, this multiplied by another summation. Now since you are doing two summation, here you change the variable, that is instead of small n, here I am making it as m. Okay, m equal to 1 to capital N, a m e power plus j only, t becomes t plus tau. So here you will be having omega naught t plus omega naught tau plus theta m. Okay, now now what we can do is, then as a next step, we can exchange this expectation with the summation. Okay, we can do expectation first and then we can do the summation. So I need to take expectation inside and summation outside. So therefore, RVV of t comma t plus tau can be written as double summation n equal to 1 to capital N, summation m equal to 1 to capital M, and we have expectation of an am. Here you can, what you can do, you can just try to put these two things together, e power minus j omega naught t plus theta n, e power plus j omega naught t plus omega naught t plus theta n, theta m here. Okay, here it is theta m, not theta n. So therefore, if you try to put all these things together, you will find that omega naught t here is getting cancelled. Therefore, you can write like this, e power j omega naught tau into e power j times of, you can write like this, theta m minus theta n. Now you can see we have like this. This 2 an am, there is no definition for an. They have mentioned an is a random variable. Whereas this part e power j omega naught tau is completely independent. There is nothing random variable here. So we can take this outside. We need not put this inside the expectation. And also you can see e power j omega naught tau. There is no m and n variable here. Therefore, you can even take this completely outside. That is outside the summation also. And here you are having e power j theta m minus theta n. So we will do this separately. Okay. So this, after organizing, we can write it as r vb of t comma t plus tau. So first step, I'm taking e power j omega naught tau as a complete outside. I have double summation, m equal to 1 to capital N, small n equal to 1 to capital N. And I am going to do expectation of am, an and am separately. This multiplied by expectation of e power j theta m minus theta n. E power j theta m minus theta n. We can write like this. Now e power j theta, we know it's a cos theta plus j sin theta. So we can write in that manner also we can complete. We can write theta cos theta plus j sin theta. Okay, so this can be further expanded. Expectation of, I write like this, cos theta m minus theta n plus j sin theta m minus theta m. Now we want to take expectation. We have no idea about a and am, so let us leave this expectation as it is. We will come to this part later. Whereas this one, expectation of theta m minus theta n, we know theta is uniformly distributed between minus pi to plus pi. That is given. Theta n is uniform distribution in the interval minus pi comma plus pi. Therefore, f theta of theta is nothing but 1 by 2 pi. So if you try to take expectation for that, you have to integrate the 2 times, right? You have to integrate the 2 times. Okay, so you have to integrate the 2 times. 1 by 2 pi into 1 by 2 pi, write it as 1 by 2 pi the whole square into cos theta m minus theta n plus j sin theta m minus theta n, integrate with respect to d theta m, d theta n for the theta ranging between minus pi to plus pi. Okay, now if you look at this one inside, cos of theta m minus theta n, sin of theta m minus theta n, when m is equal to n, we have cos of theta m minus theta n becomes 1 and sin of theta m minus theta n becomes 0. Okay, only when m is equal to n. And when m is not equal to n, this entire part will be 0 only for all ranges of theta m and theta m. When m is not equal to n, you will have entire part will be equal to 0. Therefore, you can, this becomes further simplified. Therefore, r vb of t comma t plus tau can be now easily written as e power j omega naught tau. We have double summation. But now you are going to apply n is equal to m. Therefore, you can write it as n equal to 1 to capital N, an square, expectation of an square. You can write like this. This multiplied by 1 by 2 pi the whole square, correct? Okay. Double integral of 1 into d theta m, d theta n, minus pi to plus pi, minus pi to plus pi. Now you have to do this integration. And obviously what you will get 2 pi for the first integration, again 2 pi for the second integration. So this entire part will give you the answer is 1. Therefore, r vb of t comma t plus tau is nothing but e power j omega naught tau summation n equal to 1 to capital N, you can write this expectation of an square as an square the whole bar. You can write like this. Okay, so this gives you the autocorrelation function for the given complex number. Next is power spectral density. So therefore, to find power spectral density, what you are going to do, we are going to take the Fourier transform of the autocorrelation function. So RBV of t comma t plus tau multiple with e power minus j omega tau, and you have to eliminate with respect to tau for all ranges of tau to get rho VV of omega. So from this, you can clearly understand summation a n equal to 1 to capital N, a n square bar is constant. It's not varying with the tau. So which is coming inside the integration, only e power j omega naught tau is coming into integration. E power minus j omega tau is here, d tau. So you can just write this together as what? Rho VV of omega is nothing but summation n equal to 1 to capital N, a n square the whole bar. You can write this as e power minus j omega minus omega naught tau d tau. So what is the integration of this one? Something but 2 pi del of omega minus omega naught. So what is rho VV of omega? It's nothing but summation n equal to 1 to capital N, a n square bar, this entire thing multiplied by 2 pi del of omega minus omega naught. Okay. So this is the power spectral density of the given complex random processes. Okay. So what you can do is similar procedure. You can work out one or two problems of your own interest. Okay. So next is I'm going to give you the idea about it. That is introduction about discrete random processes. So we have seen all the different thing in continuous random processes. So now we are going to extend the same concept with respect to the discrete random processes. So what is the difference in discrete random processes? Wherever you are having summation, you are going to do with integration. Wherever we are going to, so integration is going to replace with summation, and x of t will be replaced with x of a. So here you need to understand some of the formulas related to discrete geometry, some geometrical things, some formulas. Okay, some basic formulas which you have studied in discrete mathematics. Okay, so otherwise this is very easy only. So in discrete random processes, you remember the formula for discrete time Fourier transform, because whenever we are converting the random power spectral density from the autocorrelation function, you want the discrete time Fourier transform. Okay, so what is discrete time Fourier transform? Instead of integration, we are going to do summation. So understand x of t is x of n, given x of n is discrete random process. Discrete random process. Fourier transform of this is x of n. You have to multiply with e power minus j omega. You will write like this in discrete n. Instead of integration, you are going to do summation. Summation of what? You are going to eliminate n. Okay, eliminate n. So that what you are getting everything in terms of omega. So this gives you x of omega. Omega we will write like this in discrete form. Okay. So now let us do a problem directly. So you can clearly understand what is given here. Given Rxx of n equal to a power modulus n, where modulus of a lesser than 1. Find power spectral density of x of n. So question is to find rho xx of omega. Omega you please write like this. So what you need to do, take Fourier transform of Rxx of n. So Rxx of n, first you multiple with e power minus j omega, right, like this n, and we have to neglect n, right? So you are going to sum it for all ranges of n. So you get like this. Okay. So what is Rxx of n? They have given you a power modulus n, right? So what? How can you write this one? You can write this as a power minus n for n negative range, and a power plus n for positive range. So what is negative range? Minus infinity to minus 1 is negative range. 0 to plus infinity is positive range. So accordingly, you can split So now you write what is rho xx of omega is nothing but I'm splitting it directly. N equal to minus infinity to minus 1. I will write this as a power minus n. A power minus n into e power minus j omega n plus summation n equal to 0 to infinity. That is positive range a power plus n e power minus j omega n. We have like this. Okay. Now you can substitute the formula directly. So what is the formula we are going to use here is discrete mathematics formula. Remember summation a power k equal to 1 divided by 1 minus a, provided modulus of a should be less than 1 whenever k ranging between 0 to infinity. This is the standard formula in discrete mathematics which we are going to use. Okay. So now what we have to do? We are having summation. You can see the lower limit should be 0, upper limit should be infinity. So everything in the positive range. And within this you are having a power k. A power k is nothing but 1 divided by 1 minus a is the result. Okay. Provided a should be lesser than 1. Okay. So now accordingly how can you write this one? You can see the first part is this one. First part is everything is in the negative range, nothing is in the positive range. Lower limit is minus infinity, upper limit is minus 1. Whereas the second part, you can see lower limit is 0, upper limit is infinity. So it is matching with this equation. You can see. Okay, so directly I can derive the second part, but I have to first of all complete the first part, then let us complete to the second part. So what should I do? First step to come to make everything is a positive range. What should I do? Negative I have to replace with a positive. Therefore, I have to put minus as a plus. So change of variables. So change of variables, what I can do, you define m is another variable which is nothing but minus n. So wherever you are having n, you have to replace with minus m. And when n is minus infinity, what is m? M is plus infinity. When upper limit n is minus 1. When n is minus 1, what will become to m? M will become plus 1. So now change the first part. So how can you write rho xx of n? I'm changing only the first part. Summation. Now I am having n which is ranging from 1 to infinity, not from minus infinity to 1. It is becoming 1 to infinity. A power plus m. This becomes a power plus m. Here e power minus j omega n becomes e power plus j omega m plus summation n equal to 0 to infinity a power n e power minus j. So a e power minus j omega the whole power n. I'm just writing like this because I can directly substitute, right? Everything the whole power n, if I substitute, I can directly write it as 1 divided by 1 minus a. Okay. So in that form, accordingly we are organizing. Now whether can we write it directly now? We can write only the second part. First part, the lower limit is 1. But what should be the lower limit? The lower limit should be 0. Only then I can substitute this direct formula. So what can I do now? What can I do now? I can I can add a 0 here. If I'm adding 0, whatever value I get from the summation, I have to subtract here. Okay. Or you can again do change of variable. Say you define n is equal to m minus 1. Okay. So n is equal to m minus 1 when m equal to 1, n equal to 0, when m equal to infinity, n also is infinity. So you can do this change of variable. So when you do n is equal to m minus 1, what will happen? Wherever you are having m, you have to replace it with n plus 1. Wherever you are having m, you have to replace it with n plus 1. Okay. So how can I write the first part now? Summation. Lower limit becomes 0. Upper limit becomes infinity. A power n plus 1. Or can I directly, okay, e power j omega m plus 1, n plus 1 plus summation n equal to 0 to infinity a e power minus j omega the whole power n. Okay, so now what can I do? Here a power n, here a power, right? Here what I can do? Here I can take a power e j omega n outside, summation n equal to 0 to infinity a e power j omega the whole power n. I write like this part. Second part, summation n equal to 0 to infinity a e power minus j omega the whole power n. Now I can use the formula. What is the formula? Please remember, summation n equal to 0 to infinity a power k equal to 1 divided by 1 minus a. So you can directly translate, right? In both the cases, you can directly do that. So what is the answer? Let me write it. Okay. Let me write it here. Rho x of n can be written as a e power j omega n. Sorry, n will not come, right? E power j omega only. Here, e power j omega only divided by, for this part, 1 divided by 1 minus a e power j omega plus, for the second part, 1 divided by 1 minus a e power minus j omega. Okay, so this is the answer. So what you can do, if you want, you can further simplify this by multiplying both these factor and you can write in terms. So I think you should be getting the answer rho xx of omega, not n. Sorry, everywhere it is omega. Okay, rho xx of omega should be 1 minus a square divided by 1 plus a square minus 2a cos omega. So if you want, you can very well simplify. Otherwise, you can just leave it as it is. Okay. So now let us do the second problem. So you study the white noise n of n have the autocorrelation function given by Rxx of k is equal to sigma n square when k equal to 0. It means that it is R. If you try to plot Rxx of k, what do you have? You have only one part. This is sigma n square when k equal to 0. Only one spike at k equal to 0 and all the other places you are having 0. Okay. So what is power spectral density? Please understand, whenever you are having, if you take Fourier transform of this, obviously what you will get? You will be getting constant for all ranges of frequency. You'll be getting a constant. This constant value is sigma n square. Okay. So please remember this one, this del function and the constant is a Fourier transformable pairs. Okay. So obviously you should be getting only the constant. So here they are defining n of n. N of n. N is the notation for the noise. And this n which is there in the given in the square bracket is a notation for the discrete type. So it is a discrete noise. Okay. Discrete white noise. And its autocorrelation function is given. What is the question? Question is to find the power spectral density. Okay. So what you are going to do, obviously you are going to take the Fourier transform. So Fourier transform of the autocorrelation function Rn of k. You multiple this with e power minus j omega. You have to write like this into k. Eliminate k for all ranges of k minus infinity to plus infinity. You will be getting rho n of omega. Please understand I am writing omega like this. So what is this? You are having k, only at k equal to 0, you have one value. All other ranges of k, you do not have answer. So if you put k equal to 0, you get sigma n square into e power 0. E power 0 is 0. So you get Fourier 0 n of omega is nothing but sigma n square. Okay. So this is what I told you whenever you are having a spike. So this one. So always remember, whenever you are trying to integrate delta or summate delta, you will be getting the answer is 1. Okay, so this is the Fourier transform. Next, the same problem is continued. Say, now if we define a noise y of n, noise sequence, okay, y of n, which is related to white noise mentioned in the previous problem. So they have mentioned autocorrelation function and we got the power spectral density in the previous problem. We are going to use the same thing. Y of n is now defined as n of n plus b1 n of n minus 1. Okay, b1 should be some constant. Find autocorrelation function and power spectral density of y of n. So now how to do this? Solution is nothing but r y of n. They are asking you to find the r y of n comma n plus k. So how can we write this? Expectation of y of n, y of n plus k. We can write like this. So please understand, whenever we are doing continuous, we use this parenthesis. Whenever we are doing discrete, we are using the square bracket. So r y of n comma n plus k can be written as expectation of what is y of n? Capital N of small n plus b1 capital N of n minus 1. This should be multiplied with y of n plus k. So wherever you are having small n, you replace with n plus k. So capital N of n plus k into b1 times of, sorry, plus b1 times of capital N of n plus k minus 1. Okay. Now what you can do, you just multiply each factor separately. So r y of n comma n plus k now becomes expectation of first factor with the first factor will give you n of n multiplied with n of n plus k. Second factor with the first factor of the other part b1 n of n minus 1 n of n plus k. Now second part with the first part plus b1 n of n of n plus k minus 1. Now second part with the second part, so plus b1 squared n of n minus 1 plus n of n plus k minus 1. We have like this. Now what we can do, we can take the expectation separately. So you carefully look at the first part. Here expectation of this is what? Expectation of n of n plus k is what? Is nothing but r n of k. Correct? N of k, n plus k minus n plus k minus n will give you only k. Similarly, the second part you can see expectation of n minus 1, n of n plus k. So now what you are going to do? N plus k minus n minus 1. So this will give you r n of k plus 1. This should give you r n of k plus 1. The third part, expectation of n of n plus k minus 1. So this should give you n plus k minus 1 minus n. So it's nothing but r n of k minus 1. Final part, expectation of n of n minus 1 into, sorry, this is multiplication, okay, into n of n plus k minus 1. This will give you r n of k minus 1. Again here plus 1 is there, no? So n minus 1. So r n of k only. Okay. So now you can apply here. So what is r y of n comma n plus k? First part is only expectations, so r n of k. Plus second part is b1 times of r n of k plus 1. Third part is again b1 times of r n of k minus 1. b1 times of what is fourth part? Fourth part is b1 square of r n of k. So now how can you write r y of n comma n plus k? So you can see, you know what is r n of k. R n of k in the previous problem it is defined. R n of k is nothing but sigma n square only when k is 0. When k is not equal to 0, this is 0 only. So what is r n of k? R n of k is sigma n square. K is 0. Okay. And here r n of k plus 1. Only if k equal to minus 1, you will have sigma n square. Okay. So here k equal to 0, you have sigma n square. This part will give you sigma n square. Here, this part will give you b1 multiplied by sigma n squared only when k equal to -1. If only you put k equal to -1, this becomes Rn of 0. Understood? So similarly, this part, this becomes b1 times of sigma n squared only when k equal to +1. Only if you put k equal to +1, 1 minus 1 will give you 0. So Rn of 0 is sigma n squared. Here again, it becomes b1 squared when k equal to 0. So now if you try to organize, what you get, Ryy of n comma n plus k is nothing but at k equal to 0, what are the answers you are having? 1 plus b1 square times of sigma n square. b1 square sigma n square. Okay, and when k equal to -1, you have b1 sigma n square. K equal to +1, you have b1 sigma n square. This is the autocorrelation function. Now what you need to do, you need to take the Fourier transform of the autocorrelation function to get the power spectral density. Okay, so take Fourier transform of Ryy of n comma n plus k to get power spectral density. So now you can easily understand when k is equal to 0, what did I say? Summation of this one only at k equal to 0, Fourier transform will give you answer is 1. Okay. And here you are having -1, here you are having +1. Okay. So how can you write this one? Or what you can do is, you can, if you want to do it independently, you can also do it independently. Let me do it independently. Summation R yy, right? So yy of n comma n plus k, you have to multiply with e power minus j omega, right, like this, into k, and you are going to eliminate k ranging between -infinity to +infinity. You will be getting rho yy of omega. Okay. So what are the things you are having? K equal to 0, k equal to -1, k equal to +1. You do not have any other values. So when k equal to 0, Ryy of things becomes, when k equal to 0, so this is nothing but k equal to -1 to +1 only you are having answer. What is that answer? Different answer. You have to substitute it differently. All the other ranges you do not have that answer. So first what you do, you substitute k equal to 0 or k equal to -1, k equal to -1, b1 sigma n square. Okay, so b1 sigma n square into e power plus j omega k. When k equal to, sorry, +1, k equal to -1, k becomes -1. K becomes 0, Ryy of n comma n plus k. What is that answer? K becomes 0, 1 plus b1 square into sigma n square. So 1 plus b1 square into sigma n square into e power 0. K becomes 0, e power 0. Now third answer is k becomes 1. When k becomes 1, what is the answer? Here Ryy of 1 is nothing but b1 sigma n square. So plus b1 sigma n square into e power k becomes 1, right? So this is e power minus j omega. Now you can organize everything. E power 0 becomes 1. So how can you organize? Here b1 sigma n square, here also b1 sigma n square is common. So how can you organize? Rho yy of omega can be written as 1 plus b1 square sigma n square plus of b1 sigma n square into e power j omega plus e power minus j omega can be written as 2 cos omega. Okay, so you can write it as 2 cos omega also. Okay, so that is up to you. Okay, otherwise you can write like this: 1 plus b1 square sigma n square plus 2b1 sigma n square cos of omega. So this is your power spectral density. Okay, so similar procedure, the another problem I have given you, in the similar procedure only, considering a random process x of t, white Gaussian noise, here I have defined sigma n square value itself is 4. Okay, so now I have extended, instead of having only n minus 1, you are also having till n plus 1. Okay, so I have extended. So this should be actually not n, it should be actually x. You write it as x. Okay, this should be actually x, rx of k. This can be written as sigma x square, not as sigma n square. This can be written as sigma x square, which is equal to 4 when k equal to 0. So how can you proceed this? Again, to find the power spectral density of y of n, obviously you have to take the autocorrelation of y of n, then only you have to do the power spectral density. So I will just tell you the steps of proceeding. So to find the autocorrelation function Ryy of n comma n plus k can be written as expectation of y of n multiplied by y of n plus k. So wherever you are having n, keep n as it is. Wherever you are having n plus k, keep n plus k. Okay, so this can be written as expectation of what is y of n, given x of n plus 0.5 x of n minus 1 plus 0.25 x of n minus 2. This is your y of n. Okay, this entire whole thing should be multiplied with what? You should be multiplied with y of n plus k. Wherever you are having x of n, you have to now replace with n plus k. So the first part becomes x of n plus k plus 0.5 times of x of n plus k minus 1 plus 0.25 times of x of n plus k minus 2. Now what you have to do? Within expectation, you just try to multiple every part. I think you should be getting 3 plus 3 plus 3, 9 different part you should be getting. So Ryy of n comma n plus k can be written like this. See, x of n plus k plus 0.5 times of x of n minus 1 x of n plus k plus 0.25 times of x of n minus 2 into x of n plus k. Okay, I have just multiple this first part, this one with the entire thing. Now 0.5 times of x of n plus k minus 1, I have to multiple with this. Okay, so like this you should be getting. I'm just leaving this to you. I want you to complete this. Now what you have to do, you have to write, say for example, separately expectation of x of n plus k. What is this? This is nothing but n plus k minus n. So this is nothing but rxx of k. Okay, autocorrelation function, expectation of x of n into x of n plus k is nothing but autocorrelation of x of k. You just take the second part, 0.5 times of expectation of 0.5 times of, so obviously 0.5 will come outside of expectation. So expectation of x of n minus 1, x of n plus k. What is this? X of n plus k minus of n minus 1. So what will happen? This becomes k minus 1. Okay, so this is nothing but r x of not k minus 1, n plus k minus of minus. Okay, minus of n minus 1. So this becomes r x of k plus 1, not minus 1 plus 1. That is, please understand, n plus k minus of n minus 1, right? So this will give you k plus 1. So like this, you can complete. Now again, as I told you earlier, what you have to do, whenever what is rxx of k plus 1 value, rxx of k value is given. Rxx of k value is given when k is equal to 0, it is defined as 4. Okay, so what is rxx of k plus 1? Rxx of k plus 1 obviously will be equal to, please understand, given Rxx of k equal to 4 when k equal to 0, under 0 otherwise, when in all the other part k. Okay, only condition, strictly condition is k should be equal to 0. Now how will you write Rxx of k plus 1? There is a shift. This is nothing but this will take the answer 4 when only k equal to minus 1 and 0 otherwise. Understood? So because given is this one. So if only you should be having inside this, you should be having 0. So how this will become 0? Only if we put k equal to -1, this entire factor will become 0. Okay, so when only k equal to -1, you have Rx of k plus 1 is equal to 4. So you are going to solve this problem in the similar procedure what I have told you here. Okay, so carefully, instead of constant b1, here we are having some values 0.25, 0.5, that's it. Okay, so this problem is just only the extension of the previous problem. So if you carefully do part by part, see here, what is the second part? X of n minus 2, x of n plus k. So what will this give you? Expectation of x of n minus 2 into x of n plus k is nothing but Rx of n plus k minus of n minus 2. So k plus 2. This will give you Rx of k plus 2. Okay, this factor will give you Rx of k plus 2. So you can extend this problem, and with this I will stop for the discrete part also. Okay, so thank you.